Hello, and welcome to International Observe the Moon Night. I'm Jennifer Heldmann, and I am talking to you here from NASA Ames Research Center in California. I'm here at the SERVI Central Headquarters. SERVI stands for the Solar System Exploration Research Virtual Institute. And this is an institute that was created by NASA to enable researchers from around the U.S. and around the world to collaborate together studying our moon, the asteroids, and the moons of Mars, for both scientific and exploration purposes. And so since we're at SERVI, the home of this virtual institute, it only seemed appropriate that we did a virtual International Observe the Moon Night event. So thank you for tuning in today. We have a great set of speakers lined up for you, and we hope you enjoy all of the new things that you get to learn about our moon as we in the science community and the exploration communities continue to learn more about this every passing day with the continued research. So we'd like to share a little bit of that with you. So we have a slew of speakers lined up for you, and first I would like to hand it over to Dr. Yvonne Pendleton. Dr. Pendleton is the director of SERVI, so she oversees all of the activities that are happening in this virtual institute. And she'll give you a little bit of an overview of the institute itself and some of the exciting activities that have been going on and some of the new things we're learning about our moon.
Welcome, everyone. It's a pleasure to have you here tonight with us for the 2014 International Observe the Moon Night. My name is Yvonne Pendleton, and I'm the director of SERVI, the Solar System Exploration Research Virtual Institute. What is a virtual institute, you might wonder? Well, let me tell you. We have a very small central office located here at NASA's Ames Research Center in Mountain View, California. But across the United States, we have 318 researchers that are in teams. We have 9 teams across the U.S., and we have 7 international partners. And what do they all do? They work together using virtual technology. In other words, something just like this, like you and I are doing right now, to communicate. This saves a lot of money in travel, but it also makes things very efficient in terms of conveying the scientific research that they're doing. Let's go see what some of those teams look like. And here they are. Our 9 United States teams are led by principal investigators that you can see pictures of in this slide. The 9 investigators are Bill Bottke, who is from the Southwest Research Institute in Boulder, Colorado, Dan Britt, who is from the University of Central Florida, Ben Bussey, who is at the Applied Physics Lab, Johns Hopkins University, Bill Farrell, who is at NASA's Goddard Space Flight Center in Maryland, Tim Gloch, who is from Stony Brook University, Jennifer Heldmann from NASA's Ames Research Center, and Mihai Harani, who is from the University of Colorado, Boulder, David Kring from the Lunar and Planetary Institute in Houston, Texas, and Carly Peters from Brown University in Providence, Rhode Island. These are our leaders, and you've already heard a little bit from Jen Heldmann, who is running tonight's virtual International Observe the Moon Night. The principal investigators and the collaborators and the co-investigators that go with each of those teams are spread across the U.S. Here's a map that shows the different locations, and there are over 300 in total. That includes a number of students, graduate students, and postdoctoral fellows as well. Our international partners right now consist of Canada, Germany, Israel, Saudi Arabia, Korea, the Netherlands, and the United Kingdom. But wait, there's more. In September, Italy will join and be another partner with SERVI, the Solar System Exploration Research Virtual Institute. Isn't it wonderful when science can bring the world a little bit closer together? So what do we study? Well, we study the moon, which is down in the lower left-hand corner of this slide. We study near-Earth asteroids, which is on the lower right-hand side, depicted by Itokawa, one of the asteroids that we have some information about. And up at the top is an object called Phobos. Phobos is one of the 2 moons of Mars. We think that both the moons of Mars may have been asteroids that were captured by Mars a long time ago. So it makes sense that if we're trying to understand the origin and the evolution of these small bodies in our solar system, we would want to study not only the moon, but also near-Earth asteroids and the moons of Mars. I mentioned that we use virtual technology. Here's an example where we tried a big experiment about a year ago. In 2013, we held a virtual lunar science forum. Usually we do that in person, but this year we tried to do it all virtually. Every session, and we had parallel sessions going, and every poster session, everything was done in virtual mode. We had about 450 people who logged in over the course of several days to watch this. And the beautiful thing about virtual is that everything is recorded. Tonight's event is no different, and you can go on our website, servi.nasa.gov, and browse through any of the many seminars and the virtual forum that we have had in the past. And you can learn an awful lot that way. I encourage you to do that. We love being located here in Silicon Valley. The central office at NASA's Ames Research Center sits right in the heart of the place where a lot of new technology is born. And so in this picture, I wanted to show you a little bit about the new things that we're trying out. There's a little robot on the right-hand side of the screen, and that comes from a company called Double Robotics. It looks like a mini Segway to me, and it has an iPad on top of it. If you haven't seen one of these, I encourage you to look it up on the web at Double Robotics, because it's very interesting. You can use this little robot to go wherever you can't, and you can control it with your iPad or your iPhone or your computer very easily. Here we have Ricky Guest, who is the head of our information technology group, and he is showing someone how this would work. And then in the upper left-hand corner of the screen, you see what we call a water cooler conversation with the robot. The robot is being run by somebody in the Netherlands, and she was just checking us out. She came via robot. She came and walked all over SERVI central office to see what it looked like. And Teague Soderman, who's standing there by the water cooler, is our technical writer, and he was great at giving her a tour. If you're interested in a tour of SERVI, just give us a nudge on the internet. Write to us at servi.nasa.gov. There's a place where you can find the email address, and we would be glad to set up a tour for you too. Down in the lower left-hand corner of this slide, you can see what's called a hyperwall. What is a hyperwall? Well, it's a high-resolution set of screens that are a display that are tied together, a multi-screen display, and you can use them to analyze data and see things in a different way because they can be very spread out in this fashion. We always like to look for new technologies and use those in whatever way we can to communicate better with people. And tonight is a new approach for us to do a completely recorded message here for you with all of the scientists that will be bringing you fabulous talks. So I'm going to turn the microphone back over to Jen Heldmann, one of our principal investigators at SERVI, and thank you all very much for coming. We hope that you'll check us out and see all the wonderful things on the SERVI webpage, because we're here to serve you. Thank you very much. Have a good time tonight. Bye-bye.
Thanks, Yvonne, for that great talk and that overview about all the great work that's being done here at SERVI. What I'd like to do now is take this opportunity to give a brief overview about planetary conditions on the moon. So we'll talk about some of the general features of the moon just to get everyone acquainted with our nearest celestial neighbor. So a few fun facts about the moon. The moon is about 1/4 the size of the Earth and about 1/4 of a million miles away. So technically, if you think about it, the moon's within driving distance. If we could just drive up there, figure average person drives about 12,000 miles per year for 20 years, and then you'd be at the moon. The moon doesn't really have much of an atmosphere or many clouds. You're going to hear a little bit more about the moon's atmosphere in the upcoming talks. It's very, very thin and tenuous. We call it an exosphere. It's so thin. If you look at the moon, just looking with your naked eye, you can see that there are some light gray areas and some dark gray areas. Those light gray areas are called the highlands, and they're heavily cratered and they're mountainous. When you look at the dark areas, those are the maria. These are lightly cratered and they're relatively smooth, and they're mostly of volcanic origin. So just by looking at the moon, even on a clear night with your naked eye, you can see these two different types of features on the lunar surface, and they're two completely different types of geology. An interesting fact about the moon is that the rotation period equals the revolution period. So what this means is that the same side of the moon always faces the Earth. So we're always seeing the same about half of the moon, and we don't ever get to see the backside of the moon from the ground on Earth. The moon also has relatively low gravity. It's got 1/6 the gravity compared to the Earth. And you can see in this graphic, the reason for that is because the moon is smaller than the Earth, so it has less gravity. The surface temperature, there's a wide differential of surface temperatures, changing over about 260 Kelvin. It gets very, very warm on the daytime side and very, very cold on the nighttime side, whether you're in the sun or you're not in the sun. And then there are special regions near the lunar poles that are in permanent shadow, which basically have not seen the light of day. No sunlight has shone there for billions of years. And those are extremely cold areas. Some of the coldest areas in the solar system, actually, have been measured in the permanently shadowed regions on the moon. As I mentioned before, the atmosphere on the moon is super tenuous. It's so tenuous and thin, it's called an exosphere. There are some gases around the moon. I've got a little list here, and you're going to hear more about this in the upcoming few talks. But we have a source of where these gases are coming from. There's outgassing, so gases that are coming from the interior of the moon and being released. And then also sputtering, when you have micrometeorites, solar wind, electrons, etc., that are hitting the surface of the moon and knocking those gas particles out, essentially, forming this very thin exosphere around the moon. Just a reminder that we have sent people to the moon. We had 6 Apollo missions to the moon that landed successfully. And 6 missions times 2 people, each walking on the moon, means 12 astronauts have walked on the lunar surface and returned safely to the Earth. And they brought back over 800 pounds of rocks and soil. And from those samples, still to this day, an incredible amount of science is being conducted on those rocks and soil. Some of the big key points that we've learned from those samples, that those highland rocks that I talked about before solidified more than 4 billion years ago. The Maria are the volcanic rocks, as we mentioned, the darker areas on the moon, and they're a little bit younger. And by younger, I mean 3.2 to 3.9 billion years ago. So the moon is a very, very old surface, but you can see that there are age differences between the light-toned and the dark-toned regions. Here are some images to remind ourselves that we have sent humans to the moon, and hopefully we will do so again one day. And they brought, there's the little lunar rover, a little buggy car driving around the lunar surface, conducting all that great scientific investigation and collecting those rock and soil samples that were brought back for the scientific analysis to help us learn about the origin and evolution of our moon. So speaking of the origin of the moon, how did our moon come to be? Well, to go off this from a scientific manner, there are a few observations that have to be explained by any theory about the origin of the moon. So what do we have to explain? Well, first we have to explain why we even have a moon in the first place. Why do we even have a satellite orbiting the Earth? We have to explain the cratering history, which we just talked about a little bit, and I'll show you some more data on that in a second. We have to explain the low density of the moon compared to the Earth. The moon is about 3.3 grams per cubic centimeter in density, whereas the Earth is at about 5.5. So if these two objects are relatively close to each other in the solar system, why such a difference? And getting to that density issue, it's because the moon has so little metal. The metals are what make the density of our Earth a little bit higher. So why is the moon depleted in metals compared to the Earth? And the fact that the moon was once much closer to the Earth than it is now. So we have all of these things we need to explain through our theory of the origin of the moon. So what is our best thinking right now from a scientific perspective on how our moon formed? Well, we understand that the Earth originated by the accumulation and accretion of rocks and metal as our solar nebula cooled. So essentially there was a big ball of gas which started to condense in and upon itself. And this is what we call the solar nebula. And it was from this gas cloud that condensed on itself, and you have particles that are hitting each other and accreting together. Accreting means when they come together and they stick together. And you build up bigger pieces of rocks and bigger pieces, and essentially you're then building up planets and satellites. So this is how our Earth formed, and this is how the planets in our solar system formed, by the accretion of the solar nebula. As the Earth accreted, it melted from the energy of the collision. So you can imagine at very high speeds these particles that are coming together. and then you form melts. The rocks actually melt, and the chunks of material that were in there. And it was hot in this inner part of the solar system. So now we have molten material that's swirling around what is our proto-sun, which is going to become our sun. So what happens when you have molten rock is a process called differentiation. So essentially, the denser materials, the metals, sink down to the center, into the core of the Earth. And the lighter, rockier materials float to the top. And so this is how we form the structure of our planet, the core, the mantle, and the crust. So remember, we have all of this differentiation and all of these more dense metals sinking down to the bottom, and the lighter, more dense rocks float up on the top. So as this process was happening, our baby Earth was forming. An object about the size of Mars collided with the Earth. And you can imagine that's going to blast a large quantity of material out into space. And so it's blasting mantle and crustal material out into space. Now remember that we've already been going through this process of differentiation, so the mantle and the crust are relatively depleted in those more dense metals that have already sunk down to the center. So now we have this material from the rocky mantle and the crust, plus debris from that impactor itself, forming a ring around the Earth. And so now we have this process of accretion forming again, this time around our Earth. And this is the material that will accrete and eventually form our moon. So since the material that was then forming the moon had been made from material of the Earth's rocky crust and mantle, plus the impacting body, it had less metal in it than the average of all the Earth. Because remember, most of the metals had already sunk down into the center of the Earth and were not blasted out to form our moon. And so this explains why the moon has a lower density than the Earth, and it's because of its low concentration of metal as a result of the formation process. It's a nice story that all come together about the origin of our moon. So the moon accreted from this debris from the Earth's ring, so you can think about it as the moon has been born from the Earth, and it heats up to its melting point. So now the moon itself will differentiate, sending that small amount of metal that it did have to the center of the moon where it forms a small core. So remember, it's the same general processes that are happening again, accretion and differentiation, and these are the backbone of how we form planetary systems. So then what happened to the moon? Well, we have a moon now, safely in orbit around the Earth, and the moon's crust cools, and it was heavily bombarded from the remaining debris. If you think about it, you've got this ring of debris that's circling the Earth, and as the moon is forming, it's being hit by all of this material. So you have this period of this very heavy bombardment that's happening, forming a lot of craters on the lunar surface. And then as this heavy bombardment starts to subside and starts to slow down, there's volcanic activity that starts happening from these pockets of molten material that are buried down in the mantle and in the crust of the moon. So what happens is this volcanic activity that's now taking over as the dominant geologic process begins flooding the basins in the low-lying parts of the moon with lava, which covers the craters that had been previously formed in these particular areas, and forms this smooth, fresh surface, the maria. And these are the dark regions that you see on the moon that we talked about a little bit earlier. These are the volcanic features that have been filled in. And as a side note, we had similar activity occurring on the Earth, impacts, melting, volcanics, etc. So there's a very interesting geologic story that's happening in these early days of formation of the Earth-Moon system. Here's just an artist's representation. We have the Earth in the center. We have the moon that's beginning to be formed. We still have this ring of debris and gas and dust that's in the plane of the lunar orbit. And you can see the moon is still being impacted with these giant impacts, forming some of these larger craters that we see on the surface of the moon still today. So when did this all happen? Well, we know now from dating of rocks and such, this gigantic collision occurred about 4.5 billion years ago, very soon after our Earth itself had formed. So since this happened so early on in the history of the Earth's formation, this nearly molten Earth quickly healed from the impact event that ripped off this large mantle. So we don't see a big giant scar on the Earth today from this event. And this is what we call, in some, the giant impactor theory of the origin of the moon. And now it's probably the best theory that we have to explain the many properties that we see of the moon and the Earth today, and it's consistent with the laws of physics and chemistry. So it's a really interesting story to think about how our Earth and how our moon came to be. Now we talked a bit about the ages of lunar rocks and those samples that were returned from the Apollo missions. And we do this, we date these rocks by radioactive element techniques. And so what we've learned is that those cratered highlands are the oldest, the light gray areas that you see when you look at the moon, and they can be greater than 4 billion years old. And the volcanic lava rocks from the Maria are a bit younger, 3.2 to 3.9 billion years old. So the dating of these rocks gives us an absolute chronology of the history of the moon. And this is very important in our understanding of the solar system, because now we have actual dates. We know not only that the highlands formed first and are older, but we know how much older, and we can put numbers to these dates. So what happened for the rest of the history of the moon? Well, a short summary, we had this heavy bombardment period where the moon was still getting pummeled by the remaining debris from its formation. We had the formation of the Great Basins that were formed by the giant impactors, followed by the volcanic flooding with the lavas filling in some of those large basins. And then we still had some impacts that were happening, but at greatly diminished sizes and rates. And now we have a near cessation of impacts on the Earth and Moon. There are still small impacts that occur sporadically on the Moon, but the rates are greatly declined since this period of heavy bombardment towards the beginning of the formation of the Moon. And if you'd like to see in graphical form how the rate of impacting has decreased on the Moon, you can look at this plot. We have time before present in billions of years. So the 0 on the right-hand side represents the present day. And on the y-axis, we have the rate of formation of impact craters. And so you can see that early on, around 4 billion years ago, the rate of impact cratering was extremely high. And then that's when we get this cratering of the highlands that was happening. That's why the highlands are covered in craters as we see them today. Then we had some of the formation of the larger impact basins, followed by the formation of the Maria. So that's when the volcanic activity takes over and starts filling in those large basins. And now the relative rate of impact cratering is greatly lessened, and we have some recent craters that are still forming. But compared to when the moon was formed, it's a relatively quiet place up there now. We can look more closely at this critical time when we have this transition happening in the history of the moon. Remember, we have to form these Great Basins first. So those are the large impacts that form the Great Basins on the moon. And then we have the episodes of volcanic flooding of the basins and other lowland regions. And you can see this is all happening around 4 billion years ago. So a long time in the past, but we have the ability now with the age dating to actually put a number and know when this happened on the moon. If you're interested, here's a map of some of those great lunar basins that we've been talking about. These are the giant impacts that blast these big, relatively circular holes in the crust in the upper mantle of the moon. And you can see on the left-hand side, we have a map showing the names of some of these basins and the mapped out locations. And you can match those up with what you see on the moon. So you can match them with the darker areas. Those are the mare regions that we've been discussing. So one interesting thing, I think, well, why should we care about the moon? It's interesting, and that's a nice story about how it formed. But the effect of our moon on life on Earth, does it really matter to us? And so I'd like to take you through a little thought experiment here to see just how important the moon is to our own existence here on planet Earth. So it's interesting, there's a quote from Time magazine. Life arose under the hellish skies of a planet menaced by comets and asteroids. And this is essentially what we've just been talking about, this period of heavy bombardment, when the Earth-Moon system was being continuously hit by so many impacts and so many large impacts. And so you can see in this graphic right here, about 4.5 billion to 4 billion years ago or so, just getting pummeled with impacts, both the Earth and the Moon. So it was not a very nice place for anyone to live at that time. And so the heavy bombardment by comets, by meteorites, 4.5 to about, it started tapering off around 3.8 billion years ago. If life had ever tried to start that soon after our planetary system had formed, may have been killed off before it ever had a chance to really take hold. We may not know ever, but we do know that because of this period of heavy bombardment, it was not a very hospitable place in terms of habitability for life on Earth. Interestingly enough, from biologic studies here on Earth and looking at the remains of ancient life, we know that life first became established on our planet sometime between 4.4 to 3.8 billion years ago. And so it's a very interesting coincidence of events that as this period of heavy impacts and heavy bombardment started to subside, right then is when we have life emerging on Earth. So is it the case that we just needed to have a habitable enough environment that was not under these hellish skies being continually hit from above when we could have life start to arise and take hold on our planet? So it's good that we had the moon here. Another point is that the moon stabilizes our axis from our Earth itself. So if we didn't have a moon, our Earth may tilt back and forth. We see this in other planets, for example, Mars. Mars has 2 very small moons, not enough to stabilize its axis, so the tilt of Mars changes over timescales of several millions of years and longer. And so the climate on Mars can change dramatically over geologic timescales. Whereas we have a relatively large moon that's circling our planet, and that helps to keep our tilt at this nice 23.5 degrees. And so that keeps our climate relatively stable from that perspective. And so thank goodness we have our moon that's helping to keep our climate on our Earth stable enough over geologic timescales so that we could have life on Earth arise, and so that we could eventually have humans here to talk about it. So just a few things, food for thought, to think about the effects that the moon has had on allowing Earth to actually have life. So that's just my brief overview to help give us some groundwork for these future talks that we're going to hear about for International Observe the Moon Night. Thank you for listening to my talk. And what I'd like to do now is turn it over to Dr. Diane Wooden. Diane is a research scientist here at NASA Ames. She studies comets. She also studies the moon. And what she's going to be talking about today, her talk is titled Blowing in the Wind, the interaction between space weather and the moon. And so now I'd like to turn it over to Diane.
Hello, I'm Diane Wooden. I'm here to talk to you about blowing in the wind, the effects of interplanetary space weather on the moon. I'd like to acknowledge the creative assistance of Michael Drake and Brian Day, and also my colleagues and science team members of the LADEE mission. The moon is not surrounded by empty space. It's exposed to interplanetary space weather. What is interplanetary space weather? Well, it's a combination of the solar wind plasma, which is the ejection of material from the surface of the sun, as well as the solar UV photons, and the micrometeorite impacts from the background interplanetary debris cloud, called the zodiacal dust cloud, and also meteor streams that are left by the passage of comets. Galactic cosmic rays also have an impact on the moon, but we won't be discussing that today. This is a diagram of the dynamically coupled system between the sun, the solar wind, and the moon. The moon is considered to be an airless body, but it actually has a very weak atmosphere called an exosphere. We're going to be talking about the interaction between the solar wind and the debris of particles in our solar system and how that actually creates this exosphere. In particular, we'll talk about the solar wind and the solar UV. What is a solar wind? Well, it's a plasma stream of charged particles that's ejected from the sun, and it's ejected in a manner that follows the current sheets, or the multiple components of magnetic field. On the right-hand side of the diagram, you see the folded sheets of the magnetic field and the Earth-Moon system in that context. The solar wind is actually a plasma. The plasma is a fourth state of matter. We know that there's solid, liquid, gas, and plasma. You see plasma in the kind of gas globe you see, and plasma is different from a gas, because in a gas the electrons are orbiting their central nucleons. But in a plasma, it's so hot that the nucleons, or protons in the case of hydrogen, and the electrons are separated. And when the electrons and protons recombine, they produce a glow. And the color of that glow is characteristic of the color of the gas. For instance, this is neon gas, and you see these different colors in different signs, like beer signs in pubs. So the sun actually pushes off this plasma from its surface. Here we see a solar dynamics observatory movie of the magnetic field lines of the sun and the solar wind plasma gently lifting off into space. This lifting off creates the solar wind. A more strong lifting off process occurs when a magnetic anomaly, like a dark spot, recombines and creates a reconnection event on the surface of the sun, and that causes an ejection of more particles at faster speeds. These particles travel through the planetary system at about 400 kilometers per second. In fact, these particles take about 3 to 4 days to reach the Earth. In a large coronal mass ejection, or CME, it actually can disrupt satellites in low orbit, possibly. It creates aurora. It can also interrupt radio communications, and these occur more frequently at the peak of the solar cycle, for which we have just passed. In fact, the LADI mission, which I'm going to talk about, was during the part of the peak of the solar cycle. And here we see a diagram for how that plasma, or coronal mass ejection, flows out along the magnetic field lines of the sun and would hit the Earth. So what does the Earth do in response to this plasma? The Earth is largely protected from the plasma by its magnetic field. We are very lucky as a planet to have a magnetic field because it creates a magnetic bubble, or magnetosphere and magnetotail. In fact, the particles, the sun is on the left of this diagram. The solar wind particles come and try to impinge upon the surface of the Earth, but the magnetic field protects us, and those particles are caught on the magnetic field lines. You see that called a polar cusp, and the particles are then caused to go in circular orbits, releasing energy and light. I'm showing you here a movie from the Themis mission where they had 6 satellites orbiting the Earth, measuring the components of the plasma and magnetic field of the Earth. And here we see a view with time of the response of the Earth's magnetic field to the changing solar wind. And you can see that it almost looks like the Earth's magnetic field is being blown by the solar wind. When we set this in the context of the moon's orbit here is drawn to scale, that the moon orbits about the Earth, and during that orbit it spends about 6 days in the magnetic tail of the Earth. That means that the moon during those 6 days is fairly protected from the influence, or the strong influence, of the solar wind, that is protected from the particles and the electrons. I show here on the right side an astronaut artist rendition of how an astronaut might see the magnetosphere. Why would you see it glowing? Well, you have a lot of removal of electrons by the plasma interaction in the ionosphere of the Earth. And in fact, the lower right-hand corner shows the Earth imaged inside its ultraviolet glow. So you see the glow like a circle and the Earth within it. So that gives you an idea of how important our atmosphere is to protecting us from the solar wind, and how important the magnetic field is to protecting our atmosphere. Here is a diagram of the structure of the Earth's atmosphere. You see the Earth's surface marked at the bottom. You see some balloons and airplanes. That's the stratosphere. As you go up on the diagram, you see the mesosphere, the thermosphere, where the green aurora come from, and much higher up, the exosphere of the Earth. The exosphere is where the atoms and molecules are so diffuse, so tenuous, that they never collide with each other. That's the definition of an exosphere. So on the moon, the actual density of the atmosphere is like the Earth's exosphere, but the exosphere on the moon is actually touching a surface, and so it's called a surface-bound exosphere. And this is the object of our study with the LADI mission. Here I show on the left-hand side how the Earth actually stops a lot of the UV from the sun, and as well as the solar wind, which I just discussed. So in the upper corner, you see a panel that shows a yellow spectrum on top of a red spectrum. The yellow spectrum is the sunlight above the Earth's atmosphere, and the red spectrum is what gets through our atmosphere. So I've circled the region of the ultraviolet, which you know, of course, is very important for us to maintain the integrity of our atmosphere so that the ultraviolet rays are blocked, because they can cause damage to our skin. I show in the bottom panel how basically the structure of the Earth's atmosphere doesn't allow this energy to penetrate. However, for the moon, there is no atmosphere of significant density to stop the ultraviolet light. So the ultraviolet light hits the surface directly, And the photoelectric effect causes electrons to be kicked out of soil materials as well as the particles hitting directly on the surface. So here I show that on the diagram on the right that you have different sources of wind, solar wind, that is protons and electrons hitting the surface of the moon, as well as meteorites and micrometeorites, which are not burned up by any atmosphere of the moon. So the moon is exposed to these very intense particles. Well, what happens? What happens is that the atoms are ejected from the lunar soil materials into the exosphere. So it's the interaction between the interplanetary space weather that is actually creating the weak atmosphere of the moon, or the exosphere of the moon. Here I talk about sodium, because sodium has been one of the easiest atoms to measure, and has been measured from the Earth. I show a solar sodium line by giving you an example of a street lamp. That yellow glow is a very narrow wavelength made by sodium atoms. And here is an image from the National Solar Observatory of the sodium exosphere extending from the lunar surface. So sodium is a minor constituent in the rocks, but it's an atom that's very easy to be released from the rocks because it doesn't, or the soil materials, because the sodium isn't very well bound. We're interested in not only sodium, but other atoms in the atmosphere, and that's why we sent LADEE to the moon. The solar wind and particle bombardment of the moon has actually been studied by the LADEE mission, and we're currently analyzing the data. As I said, the moon has a surface-bound exosphere, and that exosphere does not have any interaction between the particles. So what exactly is happening there? Well, we're going to talk briefly about the LADEE mission, some of the results. The LADEE mission's goals was to characterize the lunar exosphere, to detect lunar dust, to test a new laser communication capability, and to demonstrate a low-cost lunar mission, and it was launched in mid-2013 and had a duration of over 100 days. The main objective was to measure the variations in composition and with time of the lunar exosphere before future lunar landings and exploration, because landings inject significant materials into the exosphere. In fact, we think that the Apollo landings of about 40 years ago we waited long enough to see those injections dissipate, and so we think that we're seeing a fairly pristine exosphere now, but as we continue to send more landers to the moon, we will perturb the atmosphere, and it will take decades for that perturbation to go away. So we want to measure it now. This is a slide that summarizes the interesting measurements that we've made of the sodium, which is unprecedented. Basically, because we orbited the moon for 100 days and had several orbits per day, up to 13 orbits per day, we were able to measure with 3 different instruments, and here I'm talking about the UV visible spectrometer. We made unprecedented systematic maps of the sodium. The ultraviolet spectrometer finds that the sodium abundance varies with lunar phase, increasing as the moon approaches its fullest. Additionally, the sodium abundance increases with meteorite showers, but it decreases when it's shaded from the solar wind by the Earth's magnetic tail. So these changes suggest a combination of sodium sources. And I'm going to talk about each of those in turn so we get a better understanding of that. In particular, I'm going to talk first about sputtering and photodesorption. So the solar wind, protons, and other heavier elements which are much less abundant, they can actually hit the soil particles and kick out atoms, which is called plasma sputtering. Also, high-energy photons can penetrate the upper nanometers or a few atomic lengths of the soil and kick out atoms as well, and that's called photodesorption. So these processes have to occur when the side of the moon is facing the sun, because the particles are charged and do not wrap around the sun. They don't wrap around the moon. They basically hit the moon directly. And also, the UV light has to hit the moon directly. So if this cartoon shows that if an atom was ejected from the day side, that it would have enough energy to go in many different directions, but if it hopped to the dark side, it would start to lose energy because the soil temperatures that it would hit would be much colder, and it would make many small hops until until the sunlight returned to that portion of the train, and then the atom would regain enough energy to start making big hops. The other thing about this cartoon is to show you that the atoms don't collide with each other, but they make ballistic trajectories like missiles would on Earth, and that they're gravitationally bound to the moon, unless they become ionized and picked up by the electromagnetic properties of the solar wind. So when we sent the Apollo astronauts to the moon, they left some experiments on the moon, and those experiments showed that the argon atoms actually created a much greater density or concentration in the atmosphere. So this slide shows from left to right, basically the sunlit side going into darkness at 90 degrees. You can see up above it says sunset to sunrise. And you see basically that the amplitude of the argon concentration in the exosphere is fairly high in the sunlit side, and then it drops significantly as the nighttime progresses, and then it rises again right before dawn and is high again in the sunlit side. So remember that the nighttime on the moon, because of the phases of the moon, is 14 days long, and the daytime is about 14 days long. That's because the face of the moon is tidally locked to facing the Earth. So as it orbits in 29¼ days, it basically takes 14 days for one particular position on the moon to experience daylight, and then it experiences 14 days of darkness. So here we show a blow-up of the diagram that we're discussing of the LADI results on the sodium observations. So on the left-hand side, we emphasize the orbital direction of the moon and have diagrams that show that at new moon, when the moon is on the left hand of the diagram, the Earth is looking at the sun, but looking at the dark side of the moon. Again, remember that the only source of light in the solar system is the sun, which is at the far left in the diagram. And so half of the moon will always be lit, and half of the Earth will be lit by the sun. And we know that the spin of the Earth causes the day-night variations that we enjoy every day, and that it takes 29¼ days for the moon to go around in that same orbital direction. So what we're showing here is on the left-hand side that at new moon, the sodium is fairly minimal. And as the moon orbits through first quarter and on to full in the clockwise direction from, say, 9 o'clock to 3 o'clock on this diagram, that the exosphere's concentration of sodium swells. It increases. And then as you go from 3 o'clock over to 9 o'clock, over the top of the diagram, in that same orbital direction, the concentration of sodium wanes. We show this in the diagram too. We've kind of drawn these sort of parabolic arcs to show the sort of modulation between new moon and full moon with a gap in the middle. We'll discuss that in a moment. The gaps are highlighted by yellow bars. So a major finding we see is that the sodium increases from new moon to full moon on the sunward day side and then decreases towards new moon. So first I'll talk about the gaps, and I've kind of darkened out the part of the parabolas that I sketched in to indicate that there's a gap in the production rate during these 6 days when the moon goes through the protective magnetotail of the Earth. What happens then is that the solar wind particles cannot impinge upon the surface. The moon is still subjected to the background of zodiacal dust cloud, but it's the impinging of the particles. Now, it's rare that the moon is actually in the Earth's shadow. We had a couple of those blood moons in the last few months where the moon was directly in the Earth's shadow. So we know it's not the sunlight effect that's causing it, it's actually the particle bombardment from the solar wind. And when you remove that particle bombardment from the solar wind, the production rate of sodium goes significantly down, and that's what these dips are in the diagram, and also shown in the graph. Dips in the graph show the dip in sodium, and in the diagram we've shown that the swelling or the amount of sodium in the exosphere diminishes. So the observation is consistent. The observation of this lunar phase dependence or lunar phase modulation of the exosphere is being modeled by the LADI science teams. Now, one of the ideas that you might come up with is, well, maybe there's an effect by the relative velocity of the moon against the background dust cloud. So here this is not a hypothesis that can be sustained, but it's just an interesting thing to think about that may have a minor effect, but not to this great extent. For instance, the Earth is moving through the background zodiacal dust cloud at about 30 kilometers per second, and the moon moves at 1 kilometer per second. So at new moon, on the left-hand side of the orbit diagram, the moon is moving counter the velocity of the Earth, so minus 1 kilometer per second with respect to this plus 30 kilometers per second. At first quarter, it's basically neutral in terms of its additive or subtractive velocity with respect to the Earth. At full moon, it's plus 1 kilometer per second. If this slight change in velocity of the moon with respect to the background zodiacal cloud, basically the Earth and the moon system are plowing through this cloud of particles, or a background zodiacal dust cloud, then we would not expect to see the sudden drop in the production of sodium during the magnetotail crossing if this was a significant effect. That is, the magnetotail does not have a significant protection for the stream of background zodiacal particles, at least that's what we think. So it seems like this is an idea that we could have considered, but the answer is no, because we do see a drop during the magnetotail crossing, so this slight difference in relative velocity cannot be the cause. We also want to point out that the Geminids meteor shower was seen as a significant increase in the sodium exosphere, and there's a couple arrows on the graph showing this enhancement over the general trend. And this is because the meteor showers are actually meteor streams of particles left by comet passages. They're fairly narrow. Usually they last 1 to 3 days, sometimes only hours. And the sodium does increase because of the increase in the rate of micrometeorite impacts. Well, this fact was known previously by observations of the moon from Earth. Here is a movie that shows kind of the steady state sodium tail. So the moon is creating sodium, and that sodium is being dragged by the solar wind away from the moon. And here's the moon at new moon configuration, where the moon's tail is passing across the Earth. And if you were to look away from the moon at new moon, so you looked at midnight, you would actually see that kind of view on the right-hand side, a steady source in the sky. Now, what happens if you have a pulse, like in a meteor shower? Well, what happens, you have a sudden increase, and you would just get a brief enhancement looking away from the sun, because, of course, again, this takes several days. This diagram is showing a several-day passage of the moon, but the meteor shower only lasts less than a day, the peak of the meteor shower. So here is a summary slide of what we just saw, that basically the data on the left shows, as we're looking away from the moon at midnight, we see an enhancement of sodium glow in the sky, that same color as you would see in a street lamp. And the model shows that this pulse of material released from the moon, the pulse of sodium atoms released into the exosphere and trailed out its tail, are then seen by Earth observers as a bright spot in the sky. And here is another cartoon video of how the Earth and the moon system are flying through the trail of particles and causing this spot to be enhanced on the sky, the spot of sodium glow of atoms due to impact vaporization. So we've seen this we've seen this from the Earth, but we haven't been able to see it in such time cadence as we did with LADI. So the ultraviolet visible spectrometer and the neutral mass spectrometer, both on LADI, have been measuring atoms and molecules in the exosphere at altitudes of 20 to 50 kilometers. Just to remind you, typical aircraft altitudes are about 15 kilometers. So this is pretty close to the surface. And that's why we were able to get such great measurements, because we dipped down close to the surface in order to see where the exosphere was enhanced. Adams revealed that the composition of the exosphere is complicated. It depends upon time and location of the surface, and it's being used to test theories for the interaction between the moon and the solar wind plasma and the flux of micrometeorites, both of which make up interplanetary space weather. What's interesting about the moon, our nearest neighbor, is that it gives us the chance to study these processes, the same processes that go on many other solar system bodies. In fact, the largest number of solar system bodies do not have atmospheres but have exospheres. We know our famous planets, but there are many, many bodies in the solar system that lack those dense atmospheres. And studying the moon gives us a chance to understand the processes that occur on many of these other bodies, including moons of outer planets and even more distant objects, the Kuiper Belt objects. So the summary is that studying the exosphere around the moon helps us understand the exospheres of asteroids and the moons of other planets. And again, our summary side that we're presenting the first results from the LADEE mission that talk about the sodium observations and how there is a cyclic production of sodium that is linked with the lunar phase that is under investigation. Thank you very much, and thank you for your excitement about observing the moon.
Thanks, Diane, for that great talk. Next on our agenda for International Observe the Moon Night, we have Dr. Ross Beyer. Ross is a research scientist here at NASA Ames and also is affiliated with the SETI Institute here in Mountain View, California. Ross works on planetary science and also is part of the Intelligent Robotics Group here at NASA Ames. And here today, Ross is going to give us a demonstration about how you can access some of the remote sensing data that we've gathered from the moon over the past several decades. So Ross will give us an overview about lunar mapping for use in mission planning and also surface operations.
Thanks, Jen. The moon, of course, is a great thing to look at through your telescope, and I hope you get a good view tonight and observe the moon. But when we think about exploring the moon, we think of the moon as a place to be, somewhere to explore. And when we think about doing that, of course, as you would perhaps when you take a trip or when you go on a vacation or when you want to explore someplace new, sometimes the first thing you reach for is a map. And we do the same thing on the moon. To help us think about how to explore better, we try and gather as much data as we can and build maps that helps us plan missions and think about how we might want to try and explore the moon. And I'm going to show you some examples of some maps that we've used to think about some possible mission scenarios on the surface of the moon, as well as how you can explore the moon on your own from your own desktop computer at home. So this map that I'm showing you here is a map of a part of the moon near the South Pole, near Hayworth Crater. And you can see I'm moving around this model a little bit. It's a 3D model, so it's not only is it a picture of what the moon looks like in that place, we've also used stereo images from the Lunar Reconnaissance Orbiter camera to make a terrain model so we know what the shape of that surface is. The red marks on the surface are places where other instruments have determined that these are areas of permanent or mostly permanent shadow. And at the south pole of the moon, there are places that have this permanent shadow that we think might be great places for volatiles or water to be trapped in. And so those are great places to explore. And so in this particular map, we built this map to think about how we might use a rover to land and explore some of these permanently shadowed regions at the south pole of the moon. And of course, when scientists want to think about doing that, scientists and engineers, we need a map like this. So we need not only a picture of the moon, what does it look like, where are the craters, where are the smooth parts, but also the shape of the moon. How is it shaped? What's the slope like? What can we drive on? What's too steep? What's too smooth? And then overlaid on that map, of course, are these red marks, which are the interesting parts, right? So you can see that this example traverse, the blue dots are places where we thought about maybe the lander would land here and it would drive to these places, the blue dots, and explore. And you can see that it drives along here and explores some of these red spots and then climbs up out of this depression because at the south pole of the moon, and it climbs up onto this hill at the end of its trip. The south pole of the moon, just like the poles of the Earth, have long periods of daylight and long periods of night. And so this low place where most of these red dots are is a place that gets dark where the sun will set on our rover, and so we kind of need to climb out. So this is an example of building a map with some information from different instruments to help scientists plan how they might drive a rover around in the south pole of the moon. And giving this information allows us to say, well, what's too steep, what's too smooth, how long is it going to take us to get from point A to point B, and what does that mean for the power and the thermal stuff on the rover. But that's kind of a brief overview of what we do with that data when we're trying to think about planning missions. But what you can do from home are actually quite a bit. You can explore the moon yourself. One of the ways to do that is by using Google Earth. This is a program provided free of charge by Google Incorporated, and they've partnered with NASA to build a couple of different planets in Google Earth you may not know about. If you load up Google Earth on your desktop computer, there's a Saturn-looking button up here at the top toolbar, and if you click on it, it shows you that there are a couple of options. You can view the night sky, you can view Mars, but of course, we're going to look at the moon tonight. So if we click on the moon, it will load up the moon as a place. And this is all data that we have assembled from NASA, and it shows lots of great stuff. If you want to learn about historic parts of the moon, so before we really got a good modern understanding, we can turn on geologic charts. And this shows you this multicolored maps of the moon where geologists have identified craters and features. And if you click on one of these maps, it shows you all kinds of great detail about that map. This is part of the USGS maps of the moon. It's a great way to explore and find out what planetary scientists think about different parts of the moon. If you're not interested in those, of course, you can just look back at your old famous plain gray moon, and you can explore other things. Of course, we have lots of data about the moon. There's a terrain map of the moon. You can turn on, you can see which parts of the moon are high and low. And you can see that here on the far side is the higher parts, and the near side is the lower blue areas where our Apollo missions landed. And of course, if you want to learn more about the Apollo missions or any of our data, there are some great guided tours that you can go, and they play a live tour that gives you some information. But you can also just explore the Apollo landing sites. I'm just going to pick Apollo 17 here. Use an overview, but if I double-click on Apollo 17, it will take us into the Apollo 17 landing site. And you can see here that we have a high-resolution image of Apollo 17. And we have marked where the spacecraft landed. And if we zoom in all the way to where the little spaceman is holding up a flag, you can see a little model of the lander there. There are panoramas that you can zoom into and explore the moon and see it in some ways, if you will, the way the astronauts saw it. You can see various things labeled. There are also some YouTube videos embedded here that show you rovers driving around or other things. It'll probably take too long to load, but you'll be able to do that and explore. And we have all of the traverses marked. So, of course, in Apollo 17, they had a lunar rover, and they drove all around the place. They drove out here to the edge of South Massif and up here, and all these different places are marked, and you can explore them. There are overviews and kind of informational bubbles about different stops on their tour. So one way to explore the moon is that way, is by using Google Earth. There are also landing sites for the Luna, the Russian Lunas and Lunokods, and other spacecraft that have landed on the moon. But the data we have here in Moon, in Google Earth, is a little outdated. And if you want to get to the most recent data of the moon, you can do that by visiting the Lunar Reconnaissance Orbiter Camera's website here at lroc.sese.asu.edu. And they have a great website here. They have featured images like this lovely image here of Lichtenberg B. But you can also explore a whole list of these featured images that they have here. So these are great stories and features about different things that the LROC camera and the science team have discovered on the moon. You can also visit global archives of all of their data. There's a great clip map and this web service. We'll go ahead and visit that and show you how you can explore some of the more recent lunar data that LROC has provided us. Footprints. And here, it'll take a while to load, I'm sure. But these show all of the places where LROC has taken pictures, high resolution, on the order of 1 meter per pixel of the moon. And you can explore those and see them in their full resolution and see what kinds of images LROC has been taking of the moon. And again, that URL to start looking at LROC images is lroc.sese.asu.edu. And you can either explore the moon on your own via their various maps and kind of explore on your own, or you can follow their featured images here on the moon. And if you have any other questions, going to International Observe the Moon Night websites is a great way to find out more about the moon. Thanks.
Thanks, Ross, for that great overview, and hopefully some of the folks now have the tools and the know-how to access some of the lunar data and start doing some exploring themselves. Next on our program agenda, we have Dr. Greg Delory. Greg is a research scientist at UC Berkeley, and he was an active participant on the LADEE mission, the Lunar Atmosphere and Dust Environment Explorer. LADEE was recently in orbit around the moon and just ended its mission to go and study the lunar exosphere. So today, Greg is going to give us an overview about the science results from LADEE and everything we've learned from this exciting mission that has been managed out of NASA Ames.
Thank you, Jennifer, for that introduction. And as Jennifer said, I've been working in the lunar program here at Ames, and it's been my privilege to be the LADEE Deputy Project Scientist. LADEE is the Lunar Atmosphere and Dust Environment Explorer, a unique, low-cost lunar mission that is revealing new things about the moon and revealing new revelations about the lunar environment that bear on how we'll explore it and how the environment may affect people in the future. So with that, I'll just continue. So LADEE was, again, a low-cost focused mission to address some very specific goals. After the Apollo missions back in the 70s, we had a set of really interesting questions left over about the nature of the lunar environment. And most people consider the moon relatively static. You know, there are craters, there's ancient lava flows and other features. But in fact, there's another aspect to the lunar environment which is more dynamic. And in fact, there's a lunar atmosphere. Most people are surprised to realize. And this is an atmosphere that we know almost nothing about. And so that was one of the key LADEE goals, was to study the lunar atmosphere. There's also some evidence that there may be an active dynamic component of dust, that is, dust moving around due to various forces on the moon. And if so, is it part of the lunar atmosphere? Is it another dynamic process that we should understand? And so that was the second goal for the LADEE mission. That was to characterize and measure the spatial and time variability of dust in the lunar atmosphere. We also had some really interesting technology and more programmatic objectives. One of the technology demonstrations was to test a high data rate laser communication system from the moon. This would give us much higher data rates and the ability to beam back a lot of data at much higher volumes on future missions. And overall, the goal of LADEE was to demonstrate that you can do what's known as a low-cost lunar mission. You can do it on a budget. You can get good science and a good technical demo out of a simple, low-cost approach that used a special multi-mission modular spacecraft bus design and really a budget and risk profile that enabled a low-cost approach and good value for scientists and the taxpayer alike. So the moon has an atmosphere. Most people are amazed to find out. It does, but it's also the truth that it's very thin. And so if you think about a cubic centimeter of the Earth's atmosphere, there are 10 to the 19th molecules. That's a lot of molecules. The atmosphere is thick on Earth. You can feel it, there's wind. But if you go down to the surface of the moon, there's only maybe 100,000 to maybe a million molecules. However, you can see it remotely using telescopic observations, and that's what that plots on the right show. That's the sodium and potassium atmosphere of the moon. And what happens is that sunlight hits the atoms in the lunar atmosphere and causes them to re-emit at specific frequencies, and it produces a glow. So there it is. That's the lunar atmosphere. It does exist, and it's something that LADEE was designed to study, and something that will apply to many other types of similar atmospheres among many other moons in the solar system. So the lunar atmosphere really is this thing called an exosphere. It's a certain type of atmosphere, and it's so thin that none of the other atoms or molecules know that each other are there. They're just bouncing around like big billiard balls. And there's a whole bunch of processes that contribute to the dynamics of the lunar atmosphere. You've got things coming in from space impacting the lunar surface. Those vaporize, and then vapor actually becomes part of the lunar atmosphere. Some of it escapes, and then some of it is gravitationally bound and stays around the moon. You also have sources within the moon from what we call interior outgassing. So if you have geothermal processes, interior processes producing heat and gas, that gas can come up and contribute to the atmosphere. And then you have a whole bunch of processes acting on the lunar surface. A cold surface, for example, will retain molecules, and a hot surface will kick them off. And you also have the effect of radiation from the sun in the form of ultraviolet photons. And then you have particle radiation, which does sputtering. And all those things kick off atoms and molecules from the lunar surface. And those atoms and molecules go on to populate the exosphere. So it's a really interesting atmosphere, basically governed by the properties of the solid lunar surface, the things that hit it, and the things that come from within the moon. So the Earth has an exosphere as well, but it's on top of an atmosphere. The Earth's exosphere is about the space station altitude and maybe a little above, whereas the lunar exosphere goes all the way down to the lunar surface. And so we call that a surface-bounded exosphere. It's a really unique, interesting type of atmosphere, and it's probably very common throughout the solar system. In fact, if you look at the moon, it's like a lot of other objects we know about. For example, the moons of the outer planets like Jupiter and Saturn. It's a lot like Mercury because it doesn't have an atmosphere. It's got a thin exosphere. And so the moon is a good test case in which to understand the unique properties of what might be the most common type of atmosphere in the solar system. And so if we can study the moon, because we know what the moon is made of and we have a lot of information about the moon, when we study the exosphere there, we have a lot of information in terms of how exospheres work, and we can probably apply that to a wide variety of other bodies. We're also interested in dust, and there's just a generic question that came out of the Apollo missions. Is there a dusty lunar sky? And the images that you're seeing here are from a lander called Surveyor 7, was on the moon in 1968. This was what was called a precursor mission. It was there before the Apollo missions came into full force to characterize the lunar environment. And one of the things that Surveyor 7 photographed was a horizon glow. That is, looking at the horizon with the sun setting behind it, this mysterious glow appeared. And there are all types of phenomena that could cause this. And the one that's most likely, in fact, is dust levitated above the surface that's scattering sunlight into the camera. And so this was termed lunar horizon glow, and is one of our first bits of evidence that there may indeed be a dynamic and active dust component operating above the moon. There's other bits of evidence as well. The sketch on the left is by Gene Cernan from the command module. He saw these strange streamers coming out from the terminator area of the moon. The streamers could be a high altitude component of dust. It's also possible that this could have been witnessing the sodium and potassium exosphere, which can give off light that the naked eye can see if you're in the dark long enough and you adjust your eyesight for dark conditions. There's also the lunar ejecta and meteorites experiment on the surface and recorded very strange activity around the terminator areas of the moon. And one interpretation of that is the large amount of dust impacting the experiment during specific times, namely around sunset and sunrise, with most of it around sunrise. So we have a couple of mysteries with the moon involving dust and the exosphere. One of the things that can move dust around is an electrically charged moon. The moon actually charges up like a giant capacitor, and on the day side it charges to a positive electric potential, and on the night side it charges to a negative electric potential. And that's because the day side you've got electrons being driven off the sun, surface of the moon by the sun, and you have the opposite problem on the night side. And so you can imagine this like building up charge when you move your feet across a carpet. You build up a charge difference between the day and the night side, and that could cause dust motion from one side to the other through electric forces. And that's one main theory for how a dynamic dust environment might exist on the moon. Okay, and so to study these interesting questions about the moon, LADEE carried a payload, which is our term for the science instruments and technology that's carried by the spacecraft, to study the lunar atmosphere and dust environment. And so the first instrument is called the neutral mass spectrometer. And that instrument literally just studies the composition of the gas around the moon. It scoops it up as LADEE flies along around the moon and analyzes its mass. And that tells us what kind of constituents are actually in the lunar atmosphere and how they vary and what their sources might be. The ultraviolet visible spectrometer is a remote sensing device. It senses ultraviolet and visible light. And this can study the resonant emissions of photons from atoms in the lunar exosphere, much like the sodium and potassium atmosphere. So it studies the atmosphere remotely, at least that component of it that emits light. And so that's a complementary way to the mass spectrometer for studying the atmosphere. And it also looks at dust. It looks at how dust around the moon might be scattering sunlight, very much like the horizon glow that we saw on the surface. And again, this is with the idea of understanding the large-scale distribution and dynamics of dust around the moon. A third instrument called the Lunar Dust Experiment actually captured and measured dust particles directly. It would do this by opening up an aperture, and the dust would fly in to the instrument, impact on a hard plate on the back end, and vaporize. And you can tell from the amount of that vapor, which actually becomes charged particles, what the mass of the dust particle was. And so that gives us an idea about the distribution and mass of the dust around the moon. I had talked about the technology demo earlier as well. This was not a science instrument, but a really cool technology demonstration for how to beam data back to the moon at much higher data rates. And this is built at MIT Lincoln Labs. And this is basically a laser on an articulated arm that points towards the Earth and fires a test pattern so we can see how to get high data rate back from the moon for future missions. So just a little bit more about the LaserCom, because it was such a great success and is a really cool and neat event for LADEE. People ask me as a scientist, how do you feel about the LaserCom? And my response to them was always, well, how did you feel when you got off of a dial-up modem and onto Comcast or DSL? It really is an orders of magnitude greater data rate than what we're used to. When we're dealing with a regular radio link, we might get as much as 50,000 bits per second, which is not too fast, really, by today's standards. With a laser communications device, we can get up 600 or more megabits, that is 600 million or more bits per second. That's a lot higher data rate and will let you beam down things like high definition images and a lot more science data. And we're really looking forward to this enabling technology. LADEE demonstrated the utility of this. We didn't actually use it for science data. We used it as a demonstration. But if we're lucky, future missions will be able to use this cool piece of technology to greatly increase the science data that we get from future planetary missions. This is the LADEE spacecraft during testing and integration, the time when we build up the spacecraft prior to launch. It's resting on its side, and you can see it has exposed areas where the solar panels have yet to be installed. So what you're seeing is a spacecraft frame, and you can see the guts inside, so to speak. Around the top, you've got navigation equipment and a couple of science instruments, both the ultraviolet visible spectrometer and the dust experimenter on the top. Then you have an avionics section that helps with managing the spacecraft. And then you have more spacecraft systems in this other segment here, and then you have the laser communications device and the neutral mass spectrometer mounted on opposite sides. The spacecraft is made out of segments that stack together, and this gives a really unique construction. This actually enabled the spacecraft to grow or shrink as we needed it to throughout the development cycle without having to redesign anything. Really useful feature for a multi-purpose, low-cost spacecraft bus. This is an image of LADI going through integration and testing in terms of the environment that we expect it to undergo in space. Before we fly anything, we need to shake it in the same way that it's going to be shaken on the launch vehicle to make sure it's mechanically robust and will survive. We also expose it to vacuum and high and low temperatures. And this just verifies that the design will survive the space environment and also the launch environment. And so everything has to be designed with that in mind. Things that are exposed to space have to survive wide temperature extremes and also some mechanical shaking during the launch phase. Speaking of the launch phase, this was the launch vehicle that we used to fly LADI. It's called the Minotaur 5, and this is another simple low-cost approach. It uses solid rocket motors, a few of which are actually left over from a time when we had intercontinental ballistic missiles. And so the first couple of stages, in fact, were from old Peacekeeper missiles, and those have been repurposed to form a launch vehicle for civilian use. Then you have additional stages as you get up towards the nose cone where LADI fits. This was launched out of the Wallops Island Flight Facility, the first lunar shot from Virginia. And here's a shot of the LADI launch. Really fantastic sight. Because it's an all solid fuel vehicle, the vehicle just leaps off the pad really quickly. We launched in the first second of the first day of our launch window, and we had a nearly flawless trajectory on our way to the moon. There's another shot from the eastern seaboard of LADI taking off. And another shot that you don't see every day, the arc of a spacecraft going up over New York. A really fantastic show for our friends and colleagues in the East Coast, and another first for LADI. So here's a little bit about the LADI mission profile. We launched on September 6th. We took about a month to get to the moon. We actually executed a number of long period orbits around the Earth before transferring to the moon. And we did that to optimize the amount of fuel that we used to get to the moon. We wanted to save as much fuel as possible for the science phase. And so it just turns out through orbital mechanics that we can optimize that by executing these phasing orbits around the Earth. And then we do what's known as a standard lunar transfer. It takes between 3 or 4 days to go from the Earth to the moon. And we entered into a checkout orbit where we could check out the spacecraft systems. And then we went down into a lower science orbit where we actually performed science observations. The entire mission was supposed to last about 180 days. We ended up lasting longer than that due to the exceptional performance by the launch team and the operations team, and also the spacecraft design being more robust than we had planned. This is a little bit about LADI's orbit. The blue line shows the highest point of LADI above the moon, and during the science phase, that changed between about 100 and 150 kilometers or so. And the red line shows the lowest altitude. And what we were doing is we were literally skimming the tops of the mountaintops on the moon. We really wanted to get as low as possible in order to observe as much as possible about the low altitude lunar atmosphere and also the dust. And so we were constantly adjusting the orbital maneuvering system to keep us low, particularly over where sunrise was on the moon, because that's where we think a lot of the interesting action is in terms of the lunar atmosphere and dust environment. And we did crash LADI into the moon, and as I tell my friends and colleagues, yes, we meant to do that. In fact, we're required to because it's a bad idea to have a spacecraft hanging out in space with no particular trajectory. So we had to literally dispose of it, which we did on an appointed time and place. As I mentioned, we were supposed to have only about a 100-day science mission, but in fact, we went considerably beyond that because we had extra fuel. And so we just kept going until the fuel got down to a low point. And then we impacted around April 18th at about 4 o'clock in the morning at Universal Time. And that was on our 2,292nd orbit after a really successful mission. And we hit the moon at 3,800 miles per hour to our amazement. And as far as we can tell, the LADEE spacecraft hit the outer rim of a crater, which makes sense. You'd hit the highest thing as you get closer down, and we probably hit that crater rim around Sunman 5. So just a quick overview of the science that LADEE did and the results so far. One interesting constituent of the lunar atmosphere is argon. One does not normally think about argon when it comes to an atmosphere, but it turns out that there's a lot of argon probably coming out from within the moon because there are geophysical processes going on that are producing it. In fact, it's likely it's caused by a radioactive decay of another constituent of the moon that produces this argon. This comes seeping up out of cracks, and it was witnessed during Apollo. However, there was another spacecraft we flew later called the Lunar Reconnaissance Orbiter that could also detect argon, and it didn't. And so we had a really interesting quandary on our hands. We had one spacecraft saying that there was argon around the moon. We had another one saying there wasn't. And LADEE's job in life apparently was to help resolve this dilemma. And in fact, we did find that there is a significant amount of argon around the moon. That was measured by our neutral mass spectrometer. And what happens is, as it comes out of the moon, it gets trapped on the lunar night side on the cold surface, kind of like your tongue getting stuck to a cold pole if you're ever playing around in winter. And then when the moon rotates around and warms up, that argon gets heated up and it comes leaping off the surface. And so what you get is essentially what amounts to an argon wind coming across a terminator of the moon. And that's just one example of the really interesting and dynamic nature of an exosphere around a small body like the moon. It's composed of all kinds of different components, and they each have their own dynamics. And we also verified from the Apollo from the ground-based measurements that there is indeed sodium and potassium around the moon. These have an abundance that seems to vary depending on the phase of the moon, and we're still trying to understand what that means. And we also see different amounts of the sodium gas in particular, depending upon whether there are meteoroid showers. And that makes some sense because we know that impactors hitting the moon and vaporizing is one source for constituents in the lunar atmosphere. So it looks like meteors are in fact contributing to the sodium component in particular. We've also seen other things around the moon like oxygen, titanium, and iron. And those are all things that are just being kicked off the lunar surface by the myriad of processes in solar radiation and space and impacts and internal processes around the moon that we're still trying to understand. LADEE's given us a good first look, and the science team will be spending some time for another year or two trying to figure out, trying to make sense of it all. Let's talk about dust. We had an idea about there being a global dynamic component of dust around the moon, possibly driven by electric charging on the lunar surface. And in fact, the lunar dust experiment did find a dust cloud around the moon. However, at this point, we don't believe it's from electrostatic charging. It confirms the idea that, in fact, most of the dust comes from the debris from small impacts, micrometeorites and other large impactors. And so this is still an important discovery. This is basically the discovery of the dust exosphere around the moon. It is variable. We see it spike up sharply whenever there's a large impactor, and then it goes back down to some low value, which is just due to the relatively constant micrometeorite flux. We're still investigating whether or not there's an electric influence on the dust. It doesn't seem obvious yet, but it's something we're continuing to investigate. So the top result far, we've seen things like argon. We've also seen neon and helium. We've seen how they vary over time. We've confirmed the presence of dust, ejecta, cloud going around the moon. We'd measure the spatial and temporal variations of the sodium-potassium exosphere and trying to make sense of what that means in terms of the source and dynamics for that part of the atmosphere. It's also interesting to note that we saw the effects of the Chinese lander, which touched down on the moon on the 14th of December. And that's an example of how fragile the lunar atmosphere is. Even the slightest disturbance from somebody else operating even very far away from you can perturb the tenuous atmosphere. And Laddie definitely detected the signs of the descent rockets from 3 as it landed on the moon. So the unanswered questions, we are just getting started. Laddie has shown that the moon is a really interesting dynamic environment with an atmosphere and dust. This is a part of the environment we're going to have to consider as we explore the moon. First, we want to understand how these atmospheres work, so we don't want to disturb them too much. And then we also need to understand how dust in particular might affect future exploration activities. And so those are the questions that the science team is looking at moving forward after the conclusion of this really exciting mission. And thank you for your time and for your interest in Laddie.
Thanks, Greg, for that great talk about the Laddie science. I think we all appreciate all the new knowledge we've gained from sending that spacecraft to the moon, and hopefully many more to come. And last but not least on our agenda for International Observe the Moon Night, we have Brian Day. Brian is based here at NASA Ames, and he works here at SERVI Central. And tonight he's going to give us an overview of lunar landforms. So these are things that you can go out and observe on the moon tonight if you'd like, so that you know where to look and what you're actually seeing. And it's always a great time having Brian give us tours of the moon, so I think that you'll enjoy his presentation as well.
Thank you very much, Jennifer, and thank you all for joining in tonight. What we're going to do is take a look at some of the features that are visible on the moon tonight, specifically for Observe the Moon Night. Now, there's a very nice map available at the International Observe the Moon Night website. And if you download that, you'll be able to see this map with descriptions of some of the interesting objects that are particularly well placed for viewing on International Observe the Moon Night this year. What we'll do tonight, though, is we will take a little bit of a closer look at each of these objects, go into them in a little bit of detail, and to do that, we're going to use a really neat tool called the Lunar Mapping and Modeling Portal, or LMMP. And this is available to you on the web. Just go to lmmp.nasa.gov. And this was a tool that was originally designed as a mission planning tool for NASA, and we still use it for such. But we've also made it available to the general public to use in a variety of things, such as, well, in this case, planning your observing sessions. So what we'll do is we'll start out, again, looking at our map. Object number 1, right here on the terminator, is an object called Mons Rumker. And Mons refers to mountain. And as we zoom in here on LMMP, you might be able to see a little bit of something showing up there. And that's because, well, this is actually a lunar volcano. And as lunar volcanoes go, well, they tend not to be very spectacular. There are no Mount Rainiers on the moon. For the most part, lunar volcanoes on the moon are very, very low-profile shield volcanoes. That's because the lava that was erupted from most of these volcanoes tended to have the viscosity of about olive oil at room temperature. And it's really hard to build a mountain out of something like that. So the lava tended to spread out over a large area, and you got a very low, flat shield, something like turning a saucer upside down and even flattening that out a bit. So what we have here is this interesting lunar volcano, but as you can see, it's not showing up in this image very well. This was taken from the Lunar Reconnaissance Orbiter, but under very low angle lighting conditions, like you have tonight, that low lighting can cause the even slightest features of topography to really stand out. And we're going to mimic that in LMMP by what we'll do here is we will bring up the laser altimetry layer here, and that will make it quite a bit more visible. So here it is here. So Rumker is actually kind of unique as lunar volcanoes go, because what it is actually an area of many domes that have layered on top of each other. So we have a collection of overlapping domes here. And let's go ahead and get an idea of its size here. So I'm going to click the line tool here to actually measure a distance across, and we can see it's about 70 kilometers. Now, something else we can do is we'll draw another line. In this case, I'm going a little further south where Rumker tends to be a little higher. And I'm going to extend on either side so we can generate an elevation profile. And here we can see the elevation profile of Rumker. So it's, 70 kilometers across and maybe only about a little over a kilometer tall. So calling that a mountain may be a little bit of a stretch in terms of what we're used to here on Earth. But this is actually one of the more spectacular, interesting volcanic areas on the surface of the moon. And again, because it is very well placed on the terminator, and we'll go back and look at our map, we can see it's right there on the terminator. That means the sun angle is coming in very, very low, and we're getting a good view. So area number 2 on our map here, I'm going to take the laser altimetry off. We'll zoom back out. Now we're going to go to the Aristarchus Plateau. And we'll zoom in a little bit here. And this is the region of the Aristarchus Plateau. And again, in kind of a low light situation, we can turn the laser altimetry back on. And you can see it's this roughly rectangular raised block of terrain. And you have the Agricola Mountains just north of it there, and you have these 2 wonderful craters, Aristarchus and Herodotus, just to the south. But this raised block of terrain here is really very interesting. It is a volcanic area. Radar signals coming off it tend to be very weak, indicating a smooth terrain. We see that there is a lack of rocks in this area. The craters that are imposed on the terrain seem to be somewhat smoothed out. This is an indicator that we have a few tens of meters of volcanic ash that is somehow accumulated in this area. And let's get a better idea of where that volcanic ash came from. If we look closely here, we'll see that there is this Schroeder's Valley, Valles Schroederi, which is the largest sinuous rill on the surface of the moon. So this is an excellent target for tonight. Look at the area of the Aristarchus Plateau and look for this beautiful example of a sinuous rill. This is actually a canyon that was carved by flowing lava that was erupted from this volcanic vent right here that is oftentimes referred to as the Cobra Head for, well, fairly obvious reasons. Again, let's go ahead and measure the diameter just going across the shortway, and we can see that that's essentially 10 kilometers across. Now, if you compare that to something like the caldera at Kilauea Volcano in Volcanoes National Park, this is quite a bit larger. So you can see we're talking about something really pretty darn spectacular here. So if you take a look, we can see how the lava erupted here in the Cobra Head and flowed out into a smaller and smaller channel and eventually spreading out across the Mare Plain there. This is not, however, the only example of a sinuous rill in the area. This is certainly the easiest one to see. But if we take a look to the northeast, we'll see that there are a number of eruptive centers on the edge of the Aristarchus Plateau, contributing a wide range of sinuous rills. So you can see a little eruptive center here and sinuous rills streaming out, another eruptive center. These are the Aristarchus rills. Over here, this is the flooded crater Prinz, and you can see a number of rills in the vicinity of Prinz too. So this is a very interesting active volcanic area. Continuing with our volcanic theme, we're going to pan to the south a little bit of the area. Well, before we do that, let's take a quick look here at these two beautiful craters, Aristarchus and Herodotus. They're very similar in diameter, but they are very, very different in morphology. Aristarchus is a much younger crater. Again, we can go ahead and measure its diameter. We can see, in this case, about 38 kilometers across. But Aristarchus has very fine detail, the typical terraced rim, a sharp central peak, whereas Herodotus is an older crater, and it has largely been flooded. The same processes that flooded the mares around it, the upwelling of thin sheets of lava, also ended up filling in a large part of Herodotus. At one point, Herodotus was a complex crater, much like Aristarchus. But because it's older and it was filled in partially by this lava, it has a very different look today. And if we do a profile across both those craters, we can see really how different they are. So here you can see the floor of Herodotus and the much deeper floor of Aristarchus. Now again, at one time, Herodotus probably had the almost identical depth as Aristarchus, but it is an older crater and it is considerably flooded. If we look a little more carefully at Herodotus, we can see something interesting. Looking at Aristarchus here, we can see ejecta, pulverized rock that was blasted out of the crater by the impact. And seeing this trail of debris, we can see some of it actually goes across Herodotus there. You can actually see that lighter spray of material going across the southern part of Herodotus. And if you look very carefully, you'll notice that we can see a larger number of small impact craters in the northern part of Herodotus than we do down here in this southern part of Herodotus, where the ejecta from Aristarchus partially flooded the crater. So again, this is a very good example of how we can tell that Herodotus is younger than Aristarchus, because we see material from Aristarchus actually overlying part of Herodotus. So now we're going to continue on a little further south, and we get to an area that, again, under normal lighting, looks very inconspicuous. But tonight, with, again, the low light level, and let's go back to our Observe the Moon map. So we've gone from Rumker to Aristarchus Plateau, and now we're going here, number 3, the Marius Hills. And again, because we're near the terminator, we should be able to get a view of these very subtle features. Again, these are examples of lunar volcanoes. And what I'm going to do is turn on the laser altimetry again. And here you can see this field of very interesting, very unusual looking volcanoes. They are not the typical low flat shields that we often see. these are actually steeper, more cone-like volcanoes. And so these could tell a story of either a more viscous lava that was erupting, or perhaps lava that was richer in volatiles, causing more of a spray and buildup of cinder cones. It's a very interesting area. There are probably about 300 of these cones. They are small in nature, but it's a really fascinating area. You can notice that there are actually some sinuous rills associated with this volcanic field on either side. These are very difficult to see through a telescope, not impossible. So consider them to be challenge objects for tonight in terms of those rills. But you should be able to pick up the cones of the Marius Hills. Now, one of the things that has been suspected for some time is that a root of dense, solidified, unerupted magma might underlie this volcanic region of the Marius Hills. And we can reveal that by bringing up another layer within LMMP. Here I'm going to go to the Kaguya probe, and we'll take a look at a gravity map. And here we see an example of a gravity map, and red indicates a higher degree of gravity, blue lower. And what I'm going to do is I'm going to adjust the transparency here of this map so we can look beneath it and see the cones. And you can see how this area of intensified gravity corresponds to the actual Marius Hills. So we can see that this is the evidence for perhaps that root of dense magma beneath this area. Now, something else that is really interesting is, well, again, these are really small features. Let's go ahead and we'll draw a line to just measure a typical width there. That's 13 kilometers. It's not a big volcano by any means. So what we are left with is the question, why on the moon do we see so many small volcanoes? On Earth we have large shields. On Mars we have gigantic shield volcanoes. But we don't readily see any large shield volcanoes on the moon. Why would the moon be so different? Well, it turns out they may well be there. A research team led by Paul Spudis in 2011 came to the conclusion that, in fact, there may be large, very low shields beneath a number of these volcanic areas. And we can illustrate that here by, again, using our elevation tool. So I'm just going to draw a line through the Marius Hills here, and we'll do an elevation plot. And we can see that, in fact, there's this large underlying structure that is quite subtle. It doesn't show up very well visibly here, even when looking at laser altimetry. But in doing the elevation plot with LMMP, we can see this large underlying shield beneath the Marius Hills. If any of you have ever been to Hawaii, to the Big Island, and you've looked across Hilo Bay at Mauna Kea, this might look familiar to you. Imagine that big, large, hulking shield with cinder cones adorning the top of it. So this is a very interesting structure that we're able to bring out here. So, not all volcanic activity on the moon creates cones or even low shields. Most of the volcanic activity on the moon resulted in these big sheets of lava filling in the mare areas. Most of these are impact basins. But if we look closely at some of these, and again, what I'm going to do here is I'm skipping to areas 9 and 10 on our map for tonight. What we're going to look at is some pyroclastic deposits. So what we'll do is we'll start out in the area here of Mare Humorum. So again, on our map, that's right down here. It's where we're looking, Mare Humorum. This is how you'll see it in your telescope tonight. And if we zoom in, you may notice right here, there's an area where the floor of Mare Humorum appears somewhat darker. And we can notice a number of rills in this area. So this is an area where we believe there were eruptions of fire fountaining lava that created ash deposits. Now what I can do here is I can change our background map here. So our base map, I'm going to change that to Clementine. We've been using an LRO map, but here I'll change it to a Clementine map. And maybe that, in this case, brings out the shading a little better. We lose a little of the fine detail, but I think the shading shows up. So look with your telescope tonight at this southwest edge of Mare Humorum and see if you can, in fact, detect that darker area that is this ash deposit, pyroclastic ash deposit. Similarly, we'll zoom back out here and we'll head north up to the Sea of Serenity. And again, looking at our map, now we're heading up here. And again, we're going to look at just the southwest edge of the Sea of Serenity. So here we are, right here, kind of near the crater Sulpicius Gallus. So we'll zoom in, and there is a darkening of the floor there. Again, let's change to our Clementine, and we can see how it's a bit darker in this area. Notice that dark patch. It's darker than the surrounding mare. So this is the pyroclastic deposit that is on the edge of the Sea of Serenity. Now, it turns out that with more and more overhead lighting, those kind of albedo differences, differences in reflectivity, become easier and easier to see. So because we have relatively high lighting here on the Sea of Serenity, this should stand out reasonably well, and you should be able to see that in your telescopes. Excuse me. So let's go back to our discussion of craters. And remember when we were talking about Aristarchus and Herodotus, and we saw how Herodotus had been partially filled in by lava. Now let's go look at a really extreme example of that. We're going to look at item number 4 on our map here, again, right on the terminator. And this is the crater Warganton. So here, in this case, in LMMP, I will use the search function. You just type in Warganton, and it will take us right to it. And I'm going to go back, let's see, so here we are at the crater Warganton. Let's switch, let's bring in our laser altimetry here real quick. And so we can see that this crater doesn't have much of a depression at all. As a matter of fact, Let's go ahead and draw a profile across it. And what we can see here is, well, the eastern rim, the southeastern rim, is definitely higher than the northwestern rim, which was essentially not there at all. But this crater is essentially a plateau. It has been filled to the brim, and if you look carefully, you can even see areas where it looks like it has overflowed. So this is an example of crater filling to a very, very high degree. So what you're looking at here is essentially a plateau on the moon caused by a crater being filled up to its rim. Again, that's the crater Wargentin, and we'll go ahead and measure a diameter for it, an idea of the size. So we're talking about essentially 80 kilometers across. It's a good-sized crater, fascinating, different type of crater to look at. So this should be a very good target for you tonight. While we are talking about craters, we'll go ahead and turn off our altimetry. We'll zoom back out. And one of the things that we'll want to take a look at tonight, and again, we'll go to our map. Right here, item number 6, is the crater Tycho. And Tycho is spectacular because it is a relatively young crater, probably about 65 million years old, and it has bright streaks of ejecta going across, in some cases, a large fraction of the moon's diameter. This is pulverized rock that was sprayed out from the impact. Let's go take a look at it in LMMP. So here it is. You can see these sprays of rock going out. It's pretty spectacular. Now, in this case, and if we zoom in, we can see that Tycho is a fine example of a complex crater, again with terraced walls and a nice sharp central peak. But because tonight it's away from the terminator, you're going to lose some of that fine topographic detail. But again, because the sunlight is coming in at a nice higher angle, that means that these albedo differences, the differences between light and dark, are such that the spray, the fine spray of rock, should become particularly evident. It's best at full moon, but we're approaching full moon, and so you can see that there is, and I'm going to switch here to the LRO. We can see that, again, there's this spray of rock going across. You can see streaks. So that's a fun thing to do tonight, is with low magnification, just see how far you and your observers can trace the sprays of pulverized rock across the surface of the moon. Going back to our map, we'll now go take a look at item number 8, which in this case is again in the Sea of Serenity, and it is the crater Linné. So heading back into LMMP, Linné is, well, not a particularly noticeable crater. Tonight, the reason you'll see it is because of a light area around it. Again, ejecta, a spray of pulverized rock that shows up well when the sun is close to overhead. But as you can see, the crater itself is not especially spectacular. It's a small crater. And this has brought about some interesting misconceptions in the past. Earlier, observers with small telescopes would see Linné as an object that was sometimes there and then sometimes disappeared. And they thought this was an indication of a changeable lunar surface, a crater that would appear and disappear. But that's really an example only of lighting. Under high angles of lighting, the albedo effect is such that you're able to really notice this spray of ejecta around it. And it stands out as one of the brighter spots on the surface of the moon. But under lower sun angles, that albedo effect is not as easy to see, and so you're left looking at this very small, inconspicuous crater in the center of the dark patch, and in many cases, people couldn't see it at all. While we're looking at ejecta coming from small craters, there's another wonderful example. It's a very fun one, and we're going to take a look here. This will be object number 7 down here. This is the crater Messier. So we'll go back into LMMP. We'll zoom out. And let's head down and look at Messier. Now again, this is going to be in a part of the moon that has very high illumination tonight. So you don't expect to see fine topographic detail in the craters. The lighting coming in is just too flat. You're not going to have good shadows to bring out topography. But because the lighting is coming at this high angle, we will be able to see the albedo features, and in this case, really interesting ejecta spray associated with the crater Messier. So let's zoom in. And what we have here, here's Messier. Messier actually consists, we have 2 craters. And the primary crater, Messier, you can see here is quite oblong in shape. And right next to it, Messier A is even stranger in shape. These shapes go back to an interesting history and discussion of the nature of craters on the moon. There was, for quite a while, a debate between whether lunar craters were volcanic in nature or impact in nature. And one of the arguments against them being impact craters was that we would expect objects to come in, meteoroids that are hitting the moon, to come in at all different angles. The vast majority of craters we see on the moon, however, are circular. And we would expect to see, according to the reasoning given, more oblong craters if these were actually caused by impacts, because so many of the impactors would be coming in not just directly overhead, but at angles. Well, it turns out that when a meteoroid hits the moon, the excavation is not done by the solid object of the meteoroid itself. It's done by the shock wave that is generated when that meteoroid first touches the surface, and that shock wave expands out spherically. So even if the meteoroid is not coming straight in, the shock wave will expand spherically from the point of impact and create a circular crater. That is, unless the angle of the impactor is very, very low. And in this case, that's what we think happened with Messier. With Messier, the impactor came in from the east at an angle of approximately 1 to 5 degrees. We believe it initially hit here at the site of Messier. Part of it broke off and formed this strangely shaped Messier A. But the really telling thing is if we zoom out, look at the streaks of debris coming out from the craters. It is not radial, but it is all in this one direction. You see this stream of debris heading out to the west. So again, this tells a story of a very, very shallow oblique impact, hitting the ground, in this case a couple of times, and spraying debris out preferentially in one direction. We'll take a look at one more really good example of this type of glancing impact, and we'll go to our map, and we're going to end up here The last item that we haven't talked about, this is item number 5 on our map, and we're going to look at the crater Schiller. And Schiller is a wonderful example of a crater that is not round at all. So let's zoom out. And, well, in this case, again, let's use our search tool. And it's always good to check your spelling. Unfortunately, we do have the spelling here on the spelling of all these features and a short description, and even some photographs of the features here on the moon map that you can download from the International Observe the Moon site. But here we're going to look at the crater Schiller. So I'll do a search for Schiller here. And here we go. So let's zoom out a little bit, and we can already see this is a pretty strange looking crater. The craters around it are fairly nice and circular, but look at Schiller. Look at how oblong it is. Very, very strange shaped crater. We can go ahead and measure a length this direction, and we see essentially 180 kilometers. We do it in the other direction. We can see 70 kilometers. So this is a very, very oblong crater. And there have been a number of interesting discussions about the origin of Schiller. Obviously, something probably came in at a very low angle. There's been some discussion that perhaps this may represent actually several overlapping craters. So maybe you had multiple impactors coming in very close to each other and hitting right next to each other, creating a series of overlapping craters. That's a possibility. One of the more intriguing possibilities, though, was raised by Charles Wood, and he notes a similarity between Schiller and several similar structures seen on Mars that have been interpreted as where previous satellites, previous moons of Mars, eventually had their orbits decay and came into a skidding stop on the surface of Mars. And the similarity between those features and this feature here has led Wood to speculate that perhaps what we're seeing here is the final resting place of where a small moon of the moon may have finally met its end. As that orbit decayed, it got smaller and smaller diameter, but as it came in, it would have come in at a very, very shallow angle. It's an interesting thing to speculate. And I invite you to think about it tonight as you look through your telescope at the crater Schiller. So again, please enjoy International Observe the Moon Night. Take a look at some of these really fascinating features. And I also hope that you will make use of the Lunar Mapping and Modeling Portal, that's lmmp.nasa.gov, to conduct your own explorations of the moon and to help plan your future lunar observing sessions. Thank you very much.
And many thanks to all of our speakers that have participated in this virtual event for International Observe the Moon Night. I hope that everyone that's been watching has learned a little bit about our moon, maybe some new things that you didn't know before. You've learned some new tools for how to access some lunar data, and now you can begin exploring yourself. So thank you again. Always a reminder to think about our nearest celestial neighbor, our moon, and thanks for tuning in.